Welcome back. The topic for this video is nuclear chemistry, and we are going to start by reviewing nuclear structure and stability. So nuclear chemistry is the study of reactions that involve changes in nuclear structure. And so keep in mind, in our nucleus we have protons and neutrons. And so some review from General Chemistry 1, the atomic number by definition is the number of protons, and we represent that by the letter Z. The mass number, represented by the letter A, is the sum of the protons and neutrons. Now remember, the atomic number you can find on the periodic table. It's a whole number. The mass number is specific depending on the isotope that you have. And so by definition, isotopes are atoms that have the same atomic number but a different mass number. And so another way to say this is that they have the same number of protons but a different number of neutrons. And that means that they have to be the same element because by definition, each element has a specific number of protons. And so a nuclide is a single type of nucleus. So it's just a single type of an isotope. And for example, you've got carbon-14. So we can represent isotopes at least 2 or 3 different ways. You've got that carbon-14, which could also be represented as the element symbol C-14. And keep in mind that that 14 is the mass number. And then another way we can represent that is with this isotope notation. And so that X just represents any element, right? So we would replace that with the element symbol. In this case, we would have carbon-14. It would be represented by a C. And then the bottom number is your atomic number. Again, number of protons from that periodic table. And so carbon has 6 protons. And I believe I've got a periodic table here. Right, so carbon, periodic table, whole number 6. And then the mass number will always be in the top left-hand corner. That's represented by 14 in this case. Okay, so 3 different ways that we can write this. Oh, and there's also a way where sometimes you may ignore that bottom number, and so it might just be represented as C14 and leave out the atomic number because it's assumed. So 4 different ways at least to write an isotope. So this is just a very quick review of fundamental forces. We don't talk about this too much, but there are 4 of them. You've got electromagnetic, gravitational, weak nuclear, and strong nuclear forces. And so nuclei are extremely dense compared to any bulk matter, right, on the order of 10 to the 14th, where the density of water is only 1. So very large difference there. And protons are positively charged, and so you're trying to keep 2 things that would normally repel each other in a very tight, dense space. And so the way you're able to overcome that is with those strong nuclear forces. And those are only going to exist in very small ranges, which is basically the size of your nuclei. So a nucleus is stable if it cannot be transformed into another configuration without adding energy from the outside. And so we get this thing called the band of stability, and you can see that in the graph on the right, and it's represented by the blue squares. And so you can kind of see right there, those blue squares will run right up in the middle of that green band. And it's the blue band that is your band of stability. Okay, the green represents all of your different radioactive isotopes that will either lie above or below that band of stability. So for lighter nuclei, the number of protons and the number of neutrons are going to be about the same. And so when we're talking about lighter nuclei, we're talking about ones right here in this region that are about 20 or less protons. Okay, so those are going, if you can tell, there's this black line on the graph right here. that black line represents a 1-to-1 ratio between your protons and your neutrons. And so you can see how that band of stability, the blue squares, starts to deviate farther and farther from that 1-to-1 ratio. Okay, but when you're down here in the lighter nuclei region around 20 or less, then that blue band of stability lies right on the 1-to-1 ratio, the black line. And so for lighter nuclei, what that means is that number of protons and number of neutrons are about the same. Now, as you get heavier, again, you see that gap start to come in between the 1-to-1 ratio and the stable nuclei band. And so eventually you'll have less protons than you do neutrons. Okay. So larger nuclei are going to have more proton-proton repulsions, and that requires a larger number of neutrons to provide that strong forces to compensate and overcome those electrostatic forces. So that's why that's happening. But what's important is just remembering, right? It's about a 1-to-1 ratio for lighter nuclei, and the number of neutrons to proton ratio will get greater as you have heavier nuclei. So nuclei that are to the left or the right of the band, and then again, that's the green area. Those are unstable. Those are going to represent radioactivity. And nuclear decay reactions are when you convert something that is unstable into another more stable isotope. So as you try to migrate closer and closer towards that blue band of stability. Okay. So let's try some quick isotope examples. Again, this is hopefully review from Gen Chem 1, but write the following isotope in nuclide notation. And so remember, that is where you have the elemental symbol, and then in the top left you have the mass number, and then in the bottom left you've got the atomic number. Okay, so the first thing that will help us will be to look up copper on the periodic table, and you'll find that the symbol for copper is Cu, but we need to know how many protons there are in a copper atom. Okay, so copper here on the periodic table is number 29, looking for that whole number. And so copper has 29 protons. And then the mass number, of course, is given in the name of the isotope. And so that 70 is equal to your mass number A, and it goes in the top left-hand corner. Okay. Determine the number of protons, neutrons, and electrons in this isotope. And it is a neutral atom. Okay, so we've already talked about how the atomic number represents the number of protons, and so the number of protons will be 29, coming from that periodic table number and from the bottom left-hand corner. If we have a neutral atom, then the number of protons will also be equal to the number of electrons, right? So number of electrons equals number of protons, and so that will also be 29. And then the number of neutrons, we're going to get that from the mass number, but remember we have to take the mass number of 70 and subtract out the number of protons, 29. So basically you're taking that top number minus the bottom number, and that will give you 41 neutrons. Okay, so we're going to skip on to the next section, nuclear equations. And we're going to look at different types of particles that are in nuclear reactions. Okay, and so there's at least 6 that we talk about in this class. There's the alpha particle. So the alpha particle is going to be a helium atom. And the alpha particle technically has a positive 2 charge, but we don't worry so much about the charge when we're looking at nuclear reactions. So that alpha particle could be represented by the element symbol for helium, or you could see the actual alpha symbol. And so it has a mass number of 4, meaning that it has 2 neutrons and 2 protons. So this is a high energy helium nuclei. A beta particle is basically going to be an electron. So remember, electrons do not carry in any significant mass compared to a proton and a neutron. So that beta particle is going to have a mass number of 0 and then -1 to represent that negative charge on electrons. And you may also see it using the beta symbol or the E for electron. Okay, but it's a high energy electron. Positrons are going to be the antimatter of beta particles, and so it's still going to be represented by the same symbol, the E, but the difference is that it now carries a positive charge but does not have any mass in comparison to protons and neutrons, and so the mass would be essentially 0. A proton is represented by a hydrogen atom, or the symbol for hydrogen, and it will have 0 neutrons, and so its mass number is 1 and number of protons also 1. A neutron will have 0 protons and have a mass number of 1, and then a gamma ray is just very high energy that's of electromagnetic radiation. Okay, so it's not going to have a mass or carry any protons with it. Okay, so these are different types of particles that can either bombard an unstable nuclei, or it could be released or emitted during a decay reaction. So when we're trying to balance nuclear reactions, it's very similar to when we balance any other type of chemical equation. So nuclear reactions follow the same conservation laws, which means that nothing can be created or destroyed, right? So the mass numbers need to be the same on both sides of the reaction, and the atomic numbers need to be the same on both sides of the reaction. Okay, so in this example here, right, if we look at the mass numbers for the reactants, you have a total of 18. And then if we add the mass numbers on the product side, those should equal 18 as well. And we can do the same thing for the atomic number, right? 7 plus 2 will give us 9, and that should be equal to 8 plus 1, which will also give us 9. Okay, so very simple process. Just make sure that the atomic numbers add up on both sides as well as the mass numbers, and that they're equivalent on the reactant and the product side. So we're going to try some examples. The first one, we are trying to determine what the missing species is. And so we're going to set up an algebraic expression where we want to compare the mass numbers first. And so we have 239 from the mass number of our reactant, plus we don't know the mass number of the other reactant, so we're going to use A and solve for A. And then on the product side, we've got the 242 plus 1 from the neutron. Okay, so just subtract 239 from both sides, and we'll get that A is equal to 4. Do the same thing for the atomic numbers. We've got 94 on the reactant side plus the atomic number for the unknown species that we don't know, and then 96 plus 0 on the product side. So subtract 94. And we get that the atomic number for the unknown species will be 2. And so if we have a mass number of 4 and an atomic number of 2. Of course, you can check a periodic table, but you know what that is. It's over here. I don't have it fully pictured, but it is helium. And so it is that alpha particle that you are releasing. Okay, so that question mark there is an alpha particle. And so, of course, you could also represent it with an alpha symbol. Okay, let's do one more. Again, we're going to add up the mass numbers on both sides. So we get 14 plus 4 equals the mass number of the unknown plus 1. So subtract 1 from both sides, and we get the mass number is equal to 17. And do the same thing for the atomic numbers. We've got 7 plus 2 equals the unknown plus 1. And so subtract 1 from both sides, and we get the atomic number equals 8. Okay, so we have a mass number of 17, an atomic number of 8. The atomic number is what we look up to determine what the element is. Look at the periodic table, find number 8 on the periodic table, and we see that that is oxygen. Okay, so this is an oxygen isotope with a mass of 17. Okay, so simple enough. Now, in this example, we're going to write some nuclear reactions just based on the description. And so we're going to end up with at least 4 reactions here. Technetium-99 is prepared from molybdenum-98. So the first step, molybdenum-98 combines with a neutron to give molybdenum-99. Okay, so let's stop there and read that sentence. We've got the MO98 starting out. And it combines with a neutron. Okay, so we know that a neutron, right, will have a mass number of 1 and 0 protons. And that gives, so that produces MO99. Molybdenum-99, as an unstable isotope that emits a beta particle. And so each time we're going to pick back up with our product and rewrite it. And it emits a beta particle. So that means on the product side we have a beta particle. And remember, we could represent that as a beta symbol, or we could represent it as an E. It's got a -1 and a 0. Okay, so either one of those would work to yield an excited form of technetium-99. So when we have an excited form, the way that we're going to represent that is with an acertic symbol, a star in the top right-hand corner. Okay, now we can look on the periodic table to go ahead and fill in what are the atomic numbers for those elements. And so we'll find molybdenum is number 42 and technetium is number 43. Okay, so we can fill in the atomic number for molybdenum at 42 and technetium at 43. And we can see that the atomic numbers, right, we've got 43 and a -1 to give us a total of 42, which matches the reactant side. Okay, so we stopped here. And then this excited nucleus relaxes to the ground state, represented as technetium-99. So we're going to pick back up with our product. And include the acertic symbol. And it relaxes to the ground state. So all that means is that we remove that, the star, by emitting a gamma ray. Okay, and so you're also going to have a gamma ray as a product. And then the ground state of technetium then emits a beta particle. And so we would have one more reaction where we start off with the ground state of technetium-99 and it emits a beta particle. Okay, so they don't tell us what the other product here is, but we can figure that out, right? Because again, On the product side, everything should add up, which means 0 plus 99 will give us the reactant side, and then something minus 1 needs to equal 43, and so that would be 44. So we keep climbing up in the periodic table. And if we look at 44 on the periodic table, we'll see that that is ruthenium. And so you've got the product ruthenium after you have a beta decay from the technetium. Okay. So last section for this video, we've got radioactive decay, which we've kind of already touched on when we were looking at those nuclear reactions, but we're just going to go a little bit more in depth here. Your parent nuclide is your unstable reactant. Your daughter nuclide is the nuclide that results from the decay, so that's on your product side. The daughter nuclide, the purpose is that it should lie closer to the band of stability than the parent. And so remember, we're constantly trying to get closer to that narrow blue band of stability. And based on where that nuclide resides in terms of the band of stability, whether it's above it, below it, or beyond it, will give us a guide as to what type of decay that it's going to undergo. Okay, so the first two types of decay that we've got is alpha decay. We've seen this. Remember, that is when you produce that helium 4 with an atomic number of 2. So when you emit a helium atom, and this happens when the daughter nuclide has a larger neutron to proton ratio than the parent. And it's going to occur primarily with heavy nuclei. So when you have a number of protons greater than 83 and you have a mass number greater than 200, that's when you're going to see the alpha decay happen. So you're typically looking for heavy nuclei for your alpha decay. A beta decay, emission of an electron, okay, that's going to happen when you have a large number of protons a large number of neutrons in comparison to your protons. So a large N to P ratio. And that means that you're going to lie above the band. So again, it's the parent that we're talking about. The parent lies above the band of stability. Then the other types of radioactive decay that we have is a gamma emission. So we saw that happen. It's when you have an excited state of something with an acertic, and so it's going to release a gamma ray while it decays down to its ground state. And so you'll see that with the parents whenever you have the star next to it. A positron emission, or the beta positive decay, a positron decay, is going to happen when you have a low neutron to proton ratio. So when you have less neutrons than you do protons, and it's going to lie below the band of stability. And again, we're talking about that parent nuclide. And then the last one is electron capture. So electron capture is also when you have a low neutron to proton ratio, and it's hard to tell whether it's positron emission or electron capture. And so for the purposes of this class, it could be both. Okay, so if you were ever asked a question, either one of those would be the correct answer if you have a low neutron to proton ratio. And then this is just a summary of what we've talked about, right? You've got alpha and beta decay, gamma decay, positron, and electron capture. And so remember, alpha decay, that is when you have a very heavy nuclei. So again, when your number of protons is greater than 83. Beta decay is going to be when you are above the band of stability, talking about that parent. So when the parent is above the band of stability. Gamma ray happens when you have an excited state, represented by that acertic symbol on the top corner right. And then positron emission and electron capture, that is when the parent lies below the band of stability. Okay, so last set of questions here. The following nuclei do not lie in the band of stability. How would they be expected to decay? And so typically the first thing that I'm looking at is whether or not I have a heavy nuclei. Okay, so do I have number of protons greater than 83? And in the first example, I do not. I have 15 protons. So I need to decide if it lies above or below the band of stability. And so I need to determine the number of protons that I have and the number of neutrons. And so the number of protons is given in that bottom corner of 15, right? That's our atomic number. And then the number of neutrons will be equal to the top number minus the bottom, right? The mass and then minus the number of protons. And so that'll give us 13 neutrons. And the number of neutrons in this example is less than the number of protons. And so that means we have a low neutron to proton ratio. And when we have that, that's an indication that we are below the band of stability. Okay, and so remember, when we're below that band of stability, so that would be somewhere in this area down here underneath, we are looking at either positron emission or electron capture, and so both of those would be acceptable answers. So we've got either positron emission or electron capture. Okay. Now in the second example, again, looking for those heavy nuclei, and we do have 92 protons, right? And so the mass number, A, is greater than 200, we're at 235, and the atomic number is greater than 83. So we have a very heavy nuclei. We're in this region up here, beyond where the band of stability ends. And so we're going to have an alpha decay. Okay, that's where you'll lose the most mass. Okay, part C, we've got significantly less than 83 protons, and so we're going to need to look at the number of protons and neutrons. So number of protons is equal to 20, and the number of neutrons is equal to 37 minus 20, which will give us 17. And so this time we have the number of neutrons is less than the number of protons. Now remember, as you were to get heavier, so if we were looking at, say, anywhere in this region here, or I guess even up here, so all of that, you would expect the number of neutrons to be greater than the number of protons. And so you have to look in a little bit more detail. But remember, if we're at about 20 protons or less, so down here at the bottom corner, then you have about a 1-to-1 ratio. And so if the number of neutrons are less than the number of protons, they should be about equivalent. Again, that means that you've got a low neutron to proton ratio because you have less neutrons. And again, that means you're below the band. And so we're looking at either positron emission or electron capture. Sorry. But if we were looking at an isotope that, let's say, had 70 protons in it, so here, it would not be as simple as a 1-to-1 ratio. Okay, so you might have to use the graph at that point to determine if you were above or below. It would not be as simple as just deciding which number that you had a greater amount of, either neutrons or protons. But with most of these, with A, with C, and with D, we're all looking at protons that are less than 20. So again, we're looking at the region down in the bottom corner. So last example, Of course, again, it's not a heavy nuclide, so we're going to have to look at the number of protons, which is equal to 3, number of neutrons equal to 9 minus 3, or 6. And so very small here, and the number of neutrons is double what we have the number of protons. And so for a small nuclei like this, that is a high neutron to proton ratio. And so you are definitely above the band of stability there. And when we're above the band of stability and we're looking at a small nuclei, that is beta decay. Okay, so remember you're releasing an electron there. Okay, so that should end the first topic on nuclear reactions.